My name is Brian Wolf. I'm director of our Operations Excellence program at LSB. I've just joined LSB Industries September of last year. Before that, I've been as part of other manufacturers helping set up data analytics, digital transformation, as you will, for this. Before that, I worked and set up for multiple clients across probably at least hundreds of facilities. LSB, we make ammonia fertilizer, that kind of stuff for agricultural, industrial clients. All right, so the classic P to F curve, right? This is what we're trying to do. We're trying to move back, predict our failures, and be able to do it in a timely manner to take action on it before you have the failure. So if you do the analytics and do all this work, but don't stop the failure, what's the point? So like she said just a second ago, getting the right information to the right person at the right time is absolutely key. And what we've utilized, we've partnered with Atonics here to do this, to grab that information, make our data smart, where it'll raise its hand, where we have some people actively looking at this information in order to catch that and move that back the P to F curve. So that's what we're trying to do. We're going to make our data smart. We're going to make our data work for us. And it's the data that we have installed at the facilities right now. We're not adding instruments right away. If you have enough data to run your plant, you likely have enough data to do analytics and monitor this process. And a big process here that as we move from the unknown state, not knowing what could potentially take you down at your facility. If you think about a facility, a couple of our size, each plant probably has 5,000 to 6,000 data points coming in real time. Where do you go look at those data? How do you find that needle in the haystack? And that's what I'm going to talk about here in a little bit. The big thing that we talk about here as well is teamwork and data transparency. Getting that information out of its little silos and bubbles so we can take action on it. So what we talked about here is making use of the existing process data first and foremost. It's there. Let's make that data smart and work for us. We want to do a rapid deployment with little effort. I don't know about y'all's companies, but we don't have a group of 10, 20 people sitting around waiting for something to do. So we want to get this quickly and effectively. And what you'll see here in a little bit, we're able to roll this out across our entire facility, fleet-wide, in 3 months, across everything. So each site's about a month, and the big process, part of that takes longer than even the deployment, is the change of management in the philosophy at the facilities. What do we do with the information now that we have it? How does it change the way we work? And then a big requirement for us was a software that drives that process, right? If you just do analytics in your little bubble and start being from corporate and there to help at the sites, that works real well sometimes until it doesn't, and usually doesn't work at all. So that's a premise here. I want to talk through this, just a little roadmap of what we outlined to do. So a couple months ago, we didn't even have data into a historian. So we need to aggregate that data and to get it in one place. I always use the term stranded data. You got to define what that means. Is it stuck in a PLC somewhere? Is it stuck in a logbook? Is it stuck in Bob's file cabinet? Or is it stuck in Jim's head? We want to get that data and get it out of those systems and into Pi, the historian that we chose. We work a lot of these in parallel, so the arrows don't make sense. I'm not great with PowerPoint, so just enjoy that. But the purpose here is to build those APR models. Some terms you can impress your friends with by is advanced pattern recognition. It's neural net math, some fancy stuff that we talk about here. But how do we predict these failures and raise that information up to the surface so we can take action on it? And then the future state, APCs and aggregating alerts together and those kind of things. So I want you to take a little mental picture of this funnel here, because I'm going to kind of reference that later here. But that's the idea. You have all your data in real time, near real time, coming into the top of that funnel. How do you filter all the noise out of that to go take action on a couple things a week? How do you go find those right things to work on? How do you do that? Well, we used a tool like Atonics. We used Atonics to do this, to build this algorithms and the models in order to drive that success. And we also built a process associated with this. And this is, again, with just our existing data. Each one of our facilities of the 3 big facilities that we have were done in 3.5 to 4 weeks, each of the sites. We just kicked off the first one today, and I'm actually missing the 2 meetings right now that we're doing to kick off on this. But in the tool, we have thousands of templates that are built. And so as part of that initial screen that we talked about, one of our goals was to aggregate our data and organize it in such a way that I can go to a pump in a facility and understand where my data is associated with that pump. What are my flows, temperatures, pressures, all those things? How can I find that? What does TE 344 mean? If I get a new process engineer, I can have him or her go to that information, and Atonics helps us build that template. We did all this without hiring data scientists or anything. So the tool itself utilizes the intelligence from engineers and the data scientists. So for a poor man's version for myself, that I can't program a thing to save my life, but I can take this tool and I've applied it to hundreds of facilities, and the ROI every year is 5+ to 1. All right. This is a big, important process too. A tool that actually drives the process of resolving issues and managing those issues through their life cycle and working on the right issues at the right time. Just because you discover something doesn't mean it needs to be shut down the plant and shut it off right now. But the workflow needs to be important into this tool and to be able to get the information in and out of the system into the tool. And that was extremely important for us as well. So come find some of the folks here and we can talk about how they actually do this. Of all the models, and a couple of the other, I did this as a consultant before, we built 50 to 60,000 models over a couple of years with minimal people, engineers, no data scientists. They didn't let me in this tool, and there was a reason for that because I could break stuff. But essentially, you have models built into this, and the templates are built so you take your whole data set from your historian and you drag and map those into the appropriate buckets. And so when you hit quick build on a model, it will deploy that model. Now we have this models don't auto learn. They can if we want, but we're engineers. We don't like auto learning on a lot of things. And we like to control what we're seeing in the model. So this is how we can get some of this stuff done really quickly. There we go. And here's kind of another view of the model. So this is probably a bearing temperature or something. And so you can see down here, the actual is blue, the expected is red, and there's kind of the statistical limits around that. But you can see how insanely dynamic that model is. Now, what that model is looking at is just what you're going to ask an operator would control how much that bearing temperature would be at that time. Rotating equipment, right? How fast is it rotating? Time of year, temperature dependent, oil analysis, those things. That's what the model template takes historically and predicts its output from that. And when it deviates from that, it pops into our system so we can review and screen these alerts in a timely manner. So that's kind of the workflow. All right. So here's the analysts that we have doing this work. So we've got a party called MFG Analytics that's doing this workflow for us. Every morning he pops in there and sees those things, that cream that's kind of raised to the top, and he will go through those every day and say, okay, yeah, I think this could be just a model retrain issue. I'm not super concerned about that. That temperature's been this way. Last week we weren't concerned about it then. Or something like this, he needs to create an issue and notify us on that. And we have weekly phone calls with our people to do this, with our team across all of operations, maintenance, leadership at the plant, the I&E techs, everybody. We have a meeting with that and our analytics team every week to drive this. And out of the same tool, we can do the diagnostics through all that process as well to understand what's going on. So he creates an issue for us in the same tool, sends it out to our group that we determined on our workflow processes and procedures. What are our rules in this process? And we will send the people that get this notification, it's both integrated with email and built into the tool. And it's all automatic, which is fantastic. So you kind of see the second guy there, Joe. You probably heard this in facilities. I don't have time to learn another tool. He didn't have to. He can hit reply from the email, say we see an issue from this tool, it goes out. His role was to take a look at this vibration. He goes out there and says, hey, look, my wire's cut on my sensor. That's why the probe's not working right now. Takes a picture of it, hits send. It uploads into the tool and automatically distributes it out to everybody in the group. So the workflow is seamless and it's wonderful. So that's kind of how it's just integrated with email. I'll skip through this. But myself here on the bottom is, how do I manage this from a program standpoint? So how do I come and say, are we working on the right things across our entire fleet? How does a small pump vibration issue go, compare with a performance issue across the plant? Well, you get it back to dollars on how it correlates to it. So I get a chance to manage this process through the same tool with understanding what's my items of importance to go work on. So here's a zoomed in view of a real life scenario that we had on a big compressor here. This is a very expensive compressor. This is a bearing temperature across this compressor. Again, actual value, blue. Expected value from the model output calculations, red. The statistical limits down there, you can kind of see what's going on here. This is where the model looks nice. And if you look at if you can read that, it was trending nicely about 170 degrees up and down every now and then. So this is happening near real time. It's about 10 minutes behind real time. So, but our goal is to catch stuff months, days, weeks, sometimes years in advance, so we can plan for it accordingly. What happened here, what's a quick quiz? What's the easiest way to break something? You shut it off and turn it on again, right? So that's what we did. We had a little outage down here. Something happened. Don't know exactly what happened. Unfortunately, on this piece of equipment, we did not believe our instruments. You ever heard that before? I'm not concerned about that. Well, the alarm point on this actually was 260 degrees. Now, you rotating people in here are probably a little cringeworthy when you see a bearing temperature at 260 degrees. I'm still tracing that one down because I don't think that's correct either. However, the alarm came in here. They didn't believe the instrument, and we had a failure right here. But look at the timelines. Middle of July, early warning, May. We could have popped the cap of this bearing, figure out what was going on here or here, and taken action. We chose not to for various reasons, but this was a good lessons learned on what we need to do with this information. And look, we've put these models across our plant. We've just deployed at this plant here 1,600 models in the last 3 weeks that are like this. These are simple to understand. Bearing temperature, simple. You can put this also on the performance of this compressor. How's your interstage stuff doing? So you can create calculated tags. Any KPI that you want, that you care about, build this in the system, have the appropriate inputs, and have the model predict the output. And as soon as it starts to deviate from this system, we can catch it real quick. One of my clients before I had this roll, and we caught a 0.1 inch change of mercury in their condenser. It swung 3 inches throughout the day from a normal cooling water temperature. 0.1, we were able to discern that with these models because it wasn't normal for that operation. So it was worth $40,000 a month to them. That's real money. But this is what we're doing across all of our facilities. Another example, I'll hit this one real quick. A bearing vibration issue. Alarm point here is right here. Nobody was even aware of this issue going on. Now we can go track this down and fix this. This is a false reading, but a false reading will still trip you in a control system. Anybody ever had that happen before? Where somebody's like, oh, I'm not worried about that's a false reading, and then boom, it trips the facility. You're down $1 million a day in production. That's real money. So what this is doing is making our data smart. It's making it raise its hand on a systematic process, and we need to change, and we are changing the way we work in that process, because if we don't take action on those things, then we end up with the same failure, and we spent money to get to that same place anyway. But that's all I had for this portion of the presentation. Come find me for the questions and everything. I think we're... This one? Not yet. It's still doing that right now. So it's an actual instrumentation reading issue. We've put some spectral stuff on it, and we think it's a wiring issue, but we don't know. All right, that's it. Thanks.